66 million years ago, a rock the size of Mount Everest slammed into the Yucatan Peninsula. It released the energy of 10 billion atomic bombs, wiped out 75% of all plant and animal life, and ended the reign of the dinosaurs. They didn't have a space program. They didn't have a choice. But we do. For the first time in the history of our planet, a species has the technology and the multi-billion-dollar infrastructure to look into the dark, identify objects on a collision course with Earth, and push them back. To understand how we stop an asteroid, we have to look at the math. This equation calculates kinetic energy. Notice how the velocity variable, the v, is squared. Because of that exponent, even a small increase in a rock's speed multiplies the explosive megatonnage upon impact. Astronomers rank these threats using the Torino scale, where 0 is completely safe and 10 guarantees global climate catastrophe. In 2004, researchers discovered Apophis, an asteroid roughly the size of the Empire State Building. It hit a level 4 on the Torino scale, the highest rating ever recorded. Surviving an object like that requires us to intervene while it's still deep in space. We have to overcome the mathematics of mass and velocity before the rock ever reaches our atmosphere. We now know Apophis won't hit Earth, but in 2029 it will pass within 32,000 kilometers of our surface. That is close enough to fly underneath our television and weather satellites. It serves as a reminder that the most dangerous asteroids are the ones we cannot currently track. Trying to spot a dark rock in the pitch black of space using a standard optical telescope is difficult. Because these telescopes rely on capturing visible light, non-reflective asteroids are easily missed against the background void. To fix this, NASA is preparing the NEO Surveyor mission. We are shifting the search from reflected light to thermal imaging, actively hunting for the heat these rocks emit as they travel through the solar system. Finding the rock only starts the clock. The specific physical strategy we deploy depends entirely on how much warning time remains. Consider a scenario where we discover a massive or fragile asteroid with several decades of lead time before impact. We use a gravity tractor. Newton's law of universal gravitation dictates every massive object exerts a pull on another. Flying a heavy spacecraft alongside the asteroid and firing thrusters creates an invisible tow line. This mutual attraction slowly drags the rock off its collision course. This method avoids explosions and high-speed impacts. With enough time, we can avert a global disaster relying entirely on the patient application of orbital mechanics. If we only have a few years' warning, we must use a faster, more direct approach, the Kinetic Impactor. This relies on the conservation of momentum. By slamming a fast, heavy spacecraft into an asteroid, we transfer enough energy to alter its velocity by just a few millimeters per second. Over millions of miles of travel, that tiny nudge ensures the rock misses Earth. In 2022, humanity tested this theory. NASA launched the DART spacecraft, crashing directly into the asteroid Dimorphos at over 22,000 kilometers per hour. The impact shortened the asteroid's orbit by 33 minutes. For the first time, our species successfully and intentionally moved a celestial body. To analyze the long-term results of that collision, the European Space Agency launched the Hera mission. Hera will arrive at Dimorphos to map the crater left by DART and measure the asteroid's mass and internal structure. DART proved that high-speed collisions can shift in orbit. Hera will provide the exact mathematical data needed to scale this technology for a true planet killer. The absolute worst-case scenario involves a massive incoming threat that is detected with less than 5 years until impact. Drilling a hole and dropping a bomb inside wouldn't work. Shattering a 10-kilometer-wide rock would merely create a radioactive shotgun blast of debris, still following the original collision course. The actual strategy is called nuclear ablation. This requires intercepting the asteroid and detonating a nuclear device in the vacuum of space, stopping short to explode just above the rock's surface. The bomb releases an intense burst of X-rays. This radiation instantly vaporizes the outer layer of the asteroid, transforming the solid rock into a rapidly expanding cloud of superheated gas. Following Newton's third law, that expanding superheated gas acts exactly like a giant rocket thruster. It violently shoves the massive asteroid in the opposite direction. Even with minimal time, our ultimate defense relies on precise redirection rather than total destruction. utilizing the fundamental laws of motion to save the planet. We have the equations, and we are building the tools. On Friday, April 13th, 2029, the universe is delivering a massive test subject right to our doorstep. As Apophis skims past, Earth's immense gravity will physically stretch the asteroid. This provides a rare opportunity to observe gravity-induced asteroid quakes in real time. NASA's OSIRIS-APEX spacecraft, which recently dropped off pristine samples of asteroid material to Earth, is currently en route to rendezvous with Apophis. It will study exactly how the flyby alters the rock's surface and orbit. We are no longer passive observers. We are actively mapping the dark, testing our defenses, and preparing for the day the sky falls. We are the first generation equipped to refuse the fate of the dinosaurs. Planetary defense is no longer a question of if we can survive, but when we will be called to prove it. If you want to keep exploring the physics that govern our universe, hit subscribe. Let me know in the comments which planetary defense method you think is the most viable. Until next time, keep looking up.